Welcome back. Previous lecture, we discussed on power quality issues. This lecture, we will focus on the harmonic distortion. Let us see the outline. We will see the introduction to harmonics. What are the fundamental of harmonics? The causes of harmonic distortion. What are their effects? The measurement techniques. How we can mitigate these techniques. Case studies we will take, and we will discuss some of the advanced topics in harmonic distortion, what are the future trends in research for harmonic distortion, and then the conclusion. So let us see what is harmonic distortion. Harmonic distortion basically refers to the presence of unwanted frequency components which are known as the harmonics in an electrical signal which deviate from the fundamental frequency. This definition we have already seen in the previous lecture as well. We have discussed that the fundamental frequency is the frequency of any country which is fixed, like for example 50 Hz for India and 60 Hz for US. So this fundamental frequency is the one which is required, but there are certain unwanted frequency which are present in this signal, and these frequencies are basically present in the integer multiples of the fundamental frequency, which are known as harmonics. So harmonics are basically the unwanted frequency signal components of the integer multiple of the fundamental frequency that are present in the electrical signal. These are basically caused by the non-linear nature of the load and the devices such as rectifiers, inverters, and switch mode power supplies. So we can see that because of the non-linear nature of the load as well as this power electronic equipments, the harmonics are basically generated. The harmonics can impact the power quality, brought down the efficiency, and affect the system performance. So harmonics have many disadvantages and they impact the quality of the power. The key point to be remembered is that the perfect sinusoidal waveform contain only the fundamental frequency, and any deviation would cause the harmonics. So we should be having only the fundamental frequency in our signal. But due to the presence of the integer multiple of these fundamental frequency, this is a deviation which is known as the harmonics. Why we want to study the harmonic distortion? Now, harmonic distortion is basically a growing problem which increasing use of the power electronic devices, which is one of the reason. So we are basically dependent on the power electronic devices like the rectifiers, inverters, filters, and so on, and they are one of the main prime reason for the harmonic distortion. The power quality which is critical for these sensitive equipment is basically impacted. There is economic impact also because the equipment damage and energy losses will take place. The standards are there like IEEE 519, which are the regulatory body, and they basically specify certain standard which we need to follow for the harmonic level. System reliability and prevent the resonance and the instability. So due to the presence of the harmonics, you can have the resonance in your system, and this may result in certain instability. Here pictorially we can see the harmonics in a sine wave. So the blue color wave is basically the sine wave, which is the pure sine wave, and due to the presence of the fundamental integer multiple of the frequency components, we can see the harmonics which are basically distorting the pure sine wave nature of the electrical wave. Harmonics in electrical system, if we talk about, then the fundamental frequency which we have discussed is either 50 Hz or 60 Hz depending upon the different countries, and the harmonics which are basically the integer multiples of these fundamental component of the frequency. So if you have the second harmonics, it means the frequency is 100 Hz. This is 2 into 50 if we take the 50 Hz as the fundamental component. If you have third harmonics, then it will be 150 Hz, 3 into 50 Hz. And these can be mathematically represented using the Fourier series. So the voltage, which is a function of time t, can have the fundamental component, which is V0, and then we can have the summation of the other components. So this is basically the DC component V0. V1 is the fundamental component, which is having the frequency omega. So omega is equal to 2 pi f, and f is basically the fundamental component of the frequency, and the other component what you have is basically in the integer multiple of these fundamental component. So these are known as the harmonics and the voltage wave, which if we want to plot it, so the voltage with respect to time t, if we want to plot it, we will not get a pure sine wave. Rather, there are a lot of harmonics which are present in the sine wave. So if we do the Fourier series visualization of this wave, then we can see that the pure fundamental frequency component, which is at 50 Hz, this is basically distorted because of the presence of the certain harmonics. It can be third harmonics or the fifth harmonics, summation of that, and we will be getting the wave which is distorted wave due to the presence of the harmonics. When we talk about the types of harmonics, then we can have odd harmonics, even harmonics, or triplet harmonics. So odd harmonics, again, we can have the third, fifth, and seventh. These are basically the most common one, and these are in the multiple of the fundamental frequency, which is 150 Hz to 50 Hz for the 50 Hz system. They are more common in power system due to the symmetrical non-linearity. So the loads are non-linear. As a result, the harmonics which are formed are basically in the odd multiple of the fundamental frequency. When we talk about the even harmonics, they will be the multiple of 2, 4, and 6. These are basically less common, often caused by asymmetrical non-linearities. So generally, most of the times you will be seeing that odd harmonics are the one which are present, and even harmonics are rare. So the triplet harmonics, the third category, which are multiples of 3, like 3, 9, and 15. So this is again a type of odd harmonics, but yes, this is multiple of 3. It is significant in three-phase system, specifically in the neutral conductors. So when we talk about the three-phase systems, so you have 3 conductors, and the triplet harmonics are also the multiple of 3, so they will be present in the neutral conductors. The important point is, in the system which is balanced for a three-phase system, the triplet harmonics are the 0 sequences and add up in the neutral conductor. So when we talk about a balanced three-phase system where the voltages in each of the phases are equal, the impedances or the load impedances are equal, so the triplet harmonics are basically the 0 sequence component of that voltage, and it will be present in the neutral conductor. If we do the spectrum analysis of these harmonics with the harmonic order varying from 1 to 13 and try to find the magnitude, so we can say that the typical harmonic content for a 6 pulse rectifier will be having the odd harmonics 5, 7, 11, and 13. For the square wave, we will have all odd harmonics, and the power electronic devices like the PWM inverter harmonics will be around the switching frequency. So where the frequency is basically switched. So we can see that if we do the spectrum analysis, the fundamental frequency is the one which is having the maximum amplitude, and then it will be keep on decreasing with the order of the harmonics. The odd harmonics are the one which is more common. The sources of these harmonic distortion are basically due to the non-linear nature of the load or different power electronic devices which are in the modern systems present. So the non-linear nature of the load, when we talk about, then it can be due to the rectifiers, which are basically the diode or the thyristor based, the SMPS, which is switch mode power supply, the variable frequency drives, the arc furnaces, fluorescent lightnings, LED drivers, electronic ballast. So these are basically the non-linear loads. Non-linear loads basically means the voltage is not proportional to the current, and because when we talk about the linear property, we follow the Ohm's law is equal to V equal to I into R. So if the voltage and current is not linear but it is exponential or some other form, then it forms the non-linear characteristic. Power electronic devices, when we talk about, then inverters, converters are basically introduce the harmonics due to the switching action, and the pulse width modulation techniques are there. We have cycloconverters and matrix converters. These topics we will discuss in very detail in the coming lectures on power electronics, advanced lecture of power electronics. But yes, these devices are the one which are the main source of harmonic distortion. There is magnetic saturation also in transformer and inductors, which is operating in saturation regions. So they are also the reason for the harmonics. If we do the rectifier analysis, so rectifiers using the diode, which is basically a single phase. If we take an example, so here we have the single phase diode bridge rectifier. So here the current harmonics, if we talk about, the harmonics can be in the current or the voltage. Let us take the current harmonics. So you will be having a discontinuous current, means the rectifier is the one which will be converting the AC supply to the DC supply, but the output that you will get is not a continuous one. You will get the discontinuous current, and it will be reached in the odd harmonics, which are the multiple of 3, 5, 7, 9 and so on. The THD level, that is the total harmonic distortion level, will be typically in the range of 30 to 80%. If you do the Fourier series analysis of these current wave, because we are talking about the current harmonics, so the current, which is a function of time t, if we write down the equations in the Fourier, then we will be seeing that apart from the fundamental frequency, we have all the odd harmonics which are present in the Fourier series expansion. PWM inverter, which is the pulse width modulation inverter harmonics. So here you can see that the sine wave is the one which is a reference, and the pulse is basically the output. So we are basically getting the PWM switching pattern, and there will be harmonics present because of this inverter action. The harmonics will be appearing around the switching frequency. At what frequency we need to produce the switching, around that only the harmonics will be there, and its multiples will be also associated with it. Lower order harmonics can be eliminated with proper PWM techniques, and trade-offs should be there between the switching frequency and the harmonic content. So when we do the switching using the power electronic devices, so at what frequency we are doing the switching, in and around that you will be having the harmonics, and yes, the harmonics can be eliminated using the proper PWM techniques. It has certain impact on the power system when we talk about, then harmonics will result in the equipment overheating, and it will be causing the losses in the transformer, the motors and the cables, increase the copper losses because you will be having the current which is I square R. It will have some heating effect and there will be a copper loss. There will be also the core losses in the transformer because you have the constant saturation effect, skin effect in the conductor at higher frequency. So lot of effect in the equipment overheating due to the core losses, the copper losses as well as the skin effect will be there. Now, since the losses are there, obviously the efficiency will be reduced and there will be more power losses. There will be overloading in the neutral conductors because of the triplen harmonics, which are the multiple of 3, and this will be accumulated in the neutral conductor in generally the 3-phase system. There will be malfunctioning of certain sensitive equipment. So such type of equipment which are very sensitive to the harmonics can interfere with the control system and the communication devices. The power factor reduction will be there because the harmonics will contribute to the reactive power. So more and more reactive power will be there, which will be lowering the power factor. Next topic, we are going to take the power factor correction, where we will discuss on these active power, reactive power, how the power factor is getting impacted. So the transformer derating due to the harmonics when we take, then the K factor calculation we need to do. So K factor calculation when we do is the harmonic order taking from 1 to infinity, and you have H square and the ratio of the current with the harmonics to the fundamental current I1 square. So the derating factor df is basically given by square root of 1 by 1 plus 0.05 k. This is the formula. And if you take an example where the k value to be 13 if you are taking, then the derating factor is 0.78, which is said that transformer must be derated to 78% of the capacity. So depending upon what load you are basically using, whether it is a linear load, fluorescent light, computer, UPS system, the VFDs, you can have different K factor associated with it, so that you need to derate it with the capacity to control these harmonics. The economic and operational impact. If we take the economic and operational impact, it will increase the maintenance cost due to overheating and premature equipment failure. So you will be having the overheating due to the harmonics, which will be impacting the sensitive equipment, and there will be failure. So obviously the cost will be impacted. Power quality issues, you will have voltage distortion effect, other loads in the system. There will be penalties associated with the regulatory, because if those are not compliance with the standard given by IEEE or ISE, then penalties will be imposed. System will go with the instability, because the harmonics can cause the resonance in the power system, and the harmonics also affect the energy measurement accuracy. So when we measure the energy, if the harmonics are present, it will not be measured with the certainty. Communication interference, if we talk about, then harmonics can interfere with the power line communication system as well. As some of the critical point, if we say the annual cost due to the poor quality of the power can reach to 4 to 6% of the total electrical energy cost. So you can see when we talk about the power quality issues, especially the harmonics, it plays a very important role in terms of the economics involved in the electrical energy costing. Now, these harmonic distortion is basically measured or quantified in terms of the THD level, which is total harmonic distortion, whether we are measuring in voltage or whether we are measuring in current. The base value for these, we will take always the fundamental component, which is the fundamental component of the voltage and the fundamental component of the current. The numerator will be having associated with all the harmonics from 2 to infinity, and the amplitude of the voltage square or the current is square. So this is the formula. Obviously it is calculated in percentage, so we are multiplying this with 100 to convert it into percentage. Total demand distortion, if you want to do it, then again this is with respect to the IL value, which is the maximum demand load current, and on the numerator side we take the harmonics from 2 to infinity. And if we calculate the individual harmonic distortion, so here we take the ratio of the harmonic current with respect to the fundamental current multiplied with 100. So for a particular harmonics, we can find out what is its distortion level. So what are basically the tools and techniques available for the measurement purpose of these harmonics? So the equipment that we generally use are the power quality analyzer, spectrum analyzer, oscilloscope with FFT capabilities. FFT means fast Fourier transform. The digital multimeters, true RMS meter, or the harmonic analyzer. So these are common lab equipments that we use for measuring the quality of the power. And the measurement points are also very important where we want to measure the power. So you have the point of common coupling, individual load terminals, transformer secondary we can incorporate, or capacitor bank location we can have for the measurement. So both the location is important and the quality of the measuring equipment is also important. Certain standards are there which we can look into, whether IEEE 519 standard, which will be limiting the harmonics for the power system. Certain IEC standards are there to determine the harmonic emission limits, as well as for the power equipment, what is the limit. So these standards need to be followed to determine what is the limit basically set by the standard for a particular equipment or in general the entire power system. The IEEE 519 harmonic limit, if we say for the TDD, which is the current distortion limit. So here if you see this table, it is shown that what should be the current distortion limit for different harmonic order. So for the harmonic order less than 11, harmonic order in the 11 to 17, 17 to 23, and so on, it is already given. So this is a chart which we need to follow, and in this chart the limits are basically specified. Voltage distortion limit, if you have the individual harmonics, so it is up to 3% if we are dealing with 69 kV system, and if you're dealing with 69 kV above, it can have the harmonics of 1.5%. THD level will have 5% in 69 kV system, and greater than 69 you can have 2.5% as the total harmonic distortion level. So this comes from the IEEE 519 limits specified for the voltage and the current and for the different harmonic order. What are the strategies that we can use to reduce this harmonic distortion? So we can use the filters. Now filters can be passive or active, and there can be have some hybrid filters as well as. So when we talk about the passive filters, it is basically the LC filter that will be absorbing the harmonic frequencies. They are cost effective because they are not bulky or and less flexible, and can create resonance issues if not properly designed, because the inductors and capacitors also contribute to the resonance. So if you do not design it properly, obviously it will be the cause for the resonance. Active filters use power electronics to inject the acting the harmonic current. So obviously the active filters are made up of power electronic devices. They are more effective but expensive and can adapt to changing load conditions. So with the change in the load conditions, these power electronic equipments which are counteracting to the harmonic currents which are present will be useful, but yes, they are more expensive. Hybrid filters are the one which is combination of the passive filters and the active filters, and you have the phase shifting transformer. This is another one strategy which can be used to reduce the harmonic distortion. It will be cancelling the harmonics in multi-phase rectifier systems, whether it is a 12 pulse or 24 pulse. So this is phase shifting transformer. So if we see the passive filter design for a single tuned filter, now it is a LC network. Here you can see, and the frequency response, if you see it, then here you can see the resonance. So the resonant frequency is obtained as 1 by 2 pi under root LC for the tuned filter, and the quality factor is given by 1 by R under root L by C. So passive filter design we can do for the harmonic control. Active power filter operation, we can have the shunt active power filter principle, where you have the non-linear nature of the load, and since it is a shunt type, shunt means parallel, so you are putting active power filter in parallel with the non-linear load. So whatever the current which is coming, that's the source current from the voltage source, will be distributed from the non-linear load and the active power filter. So this active power filter will generate the harmonic current which is equal and opposite to the load harmonics. So this non-linear load will have certain harmonics, and the active power filter will be generating certain currents which will be counteracting or equal and opposite to the load current. Source current will become sinusoidal. So whatever the source current you have, this is due to the presence of the harmonics, this can be impacted, but yes, active filter, when we use it, it will become sinusoidal. Real-time harmonic detection and compensation is also possible when the system is under function with the automatic process using the active filters. So multi-phase rectifier system, you have whether it is a 12 pulse rectifier, 24 pulse rectifier, then here you can see the harmonic order with the relative amplitude for the multi-phase system. So we are basically using the phase shifting transformer to eliminate these harmonics, whether it is a fifth harmonic, seventh harmonics, because the odd harmonics are the one which will be generally present in the system due to the power electronic equipments, and they will be non-linear nature. Lowest harmonics will be 11 and 13, and the THD will be reduced from 30% to 10% in 12 pulse rectifier. If you use 24 pulse rectifier, further harmonic reduction can be possible with the lowest harmonic, basically 23rd and 25th. THD can be brought down to less than 5%. PWM techniques for harmonic reduction, there are different PWM techniques suggested. One is sinusoidal PWM, space vector PWM, selective harmonic elimination and random PWM. So lot of PWM techniques are there. Generally here we are just introducing you the terms, and in other coming lectures in detail we will discuss on this. So sinusoidal PWM basically will have the triangular carrier versus the sinusoidal reference. Harmonic will be appearing around the switching frequency. Whereas space vector PWM, you can have better DC bus utilization and you can bring down the harmonic to lower level distortion. You can have certain selective harmonic elimination using the pre-calculated switching angle. It will be eliminating specific low order harmonics. Because generally third harmonics or the fifth harmonics, which are low order harmonics, they can be eliminated easily using the selective harmonic elimination. Random PWM will be spreading the harmonic energy across the frequency spectrum, and this will reduce the acoustic noise which are generally present with the equipments. So PWM technique is one of the powerful technique for harmonic reduction. If you talk about the other mitigation approach, you can have the line reactors, which is basically to add the inductance to smooth the current waveform. So you are having the inductor which you are adding, the current waveform will be smooth, and typically it will have the 3 to 5% impedance to reduce the current harmonics by 25 to 50%. So line reactors is again one technique. Isolation transformer, K-rated transformer, you can do the load management, power factor correction, you can do it, and you can also comply with certain standard to have different mitigation approach. So these techniques are very important. When we do the power factor correction, the aim is to control the load angle. So power factor angle we are controlling so that the reactive power can be reduced. You can have different standards, IEEE or ISC standard, and see those standard. Whatever the non-linear nature of the load are there, you can distribute it so that we can minimize the harmonic impact, and good K-rated transformer we can design to handle the harmonic load. So the design rule says that always check for resonance between power factor correction capacitors and system inductances. So resonance plays a very important role in harmonics. So we have to check this harmonics, what are the order of the resonance present in the capacitor and the system inductance. We'll take certain case studies. Case study 1, where we talk about the industrial plant using the variable frequency drives. So what was the scenario? The manufacturing facility with 50 variable VFD experiencing transformer overheating and premature failure. So the case that was appearing is basically the overheating issue, the premature failure issue, because of the presence of the variable frequency drives. So initially we need to measure. What we need to measure is basically the current distortion, which is 28%, and it is obviously exceeding the limit of IEEE, which is 8% basically allowed. So the dominant harmonics is basically the fifth one, which is comprising the 18%, 7th harmonic the 12%, and 11th harmonic is the 8% of the fundamental frequency. Transformer K factor is determined to be 15.2, originally rated for K equal to 4, and power factor is degraded to 0.72. So this is basically the initial measurement. Now we will take out the solution. So what is the solution? You install the 5th and 7th harmonic tuned passive filters. So the solution that we bring out is basically use of the passive filters with the 5th and the 7th harmonics, because you can see here the 5th and the 7th harmonics are the one which is more dominating here, and hence it will be we can add certain line reactors 5% to all the VFD inputs and upgrade the transformer to K13 rated input. So yes, the solution has been taken. So what is the result? We got it. The THD level is reduced to 6.8%. Power factor is improved to 0.94. So initially the power factor was 0.72. Now the power factor has come to 0.94. So power factor improvement is there. Transformer temperature is reduced by 25 degrees centigrade, and you have a good amount of annual energy saving around $45,000. So this is again the annually. So you can see here from this case study that industrial plant with VFD, and due to the presence of the harmonics, impact was there, and the solution what we try to achieve is using the passive filters. Case study 2 we will take with the data center where the power quality issue has taken place. So the scenario is there is a large data center which is having the UPS system and the server load, and it is experiencing the neutral conductor overrating. So this is what the engineers have found out, and they have done certain problem analysis. What is the analysis they have done is basically the triplen harmonic component are present which are high. We have seen the triplen harmonics means the third component and its multiples will be there. So third harmonic comprise 45%, ninth harmonic is having 15%. So the neutral current, which is 180% of the phase current, and there is a frequent UPS bypass operation, server equipment malfunctioning is there. So these are causing the damage. What solution has been taken to deal with this? We installed the zigzag transformer for triplen harmonic mitigation. So zigzag transformer is the one which the solution is provided, so that the triplen harmonics which are present about third harmonics and the nine harmonics can be counteracted. It is upgraded so that the neutral conductors to 200% of the phase conductor side. So the neutral conductors are taken out and new conductors have been put down, which is 200% of the phase conductor side. So we implement active harmonic filter at main distribution panel. Again, the filters are also used which are active, and load balancing is also there across the phases because it is a three-phase system. So the load which are present across the phases, it has to be balanced, then the current will also be balanced. Now what is the outcome? So neutral current is reduced to 15% of the phase current. Earlier it was 180% and now it has come to 15%. Improved the reliability and the equipment lifespan, and we comply with the standard given by IEEE 519, which is achieved. So yes, with this case study, what we have taken for data center, the outcome is quite good. Case study 3, let us understand for a hospital, which is a critical power system, what is the challenge? The medical equipment which are sensitive to harmonics, you have the LED lightning retrofit created harmonics, imaging equipment interference, and in emergency power system affected. So this challenge is basically faced by a hospital which is one of the critical power system center, and measurement when we do it, we found out that the harmonics level for the voltage harmonics is 8.2%, whereas the limit is set to be 5%. So it is exceeding it. Third harmonics comprise 6.8% and fifth harmonic comprise 4.2%. So solution which was given is basically with the use of isolation transformer for the critical load, harmonic mitigation transformers are also used, dedicated circuits for sensitive equipment, and power conditioning units. So these are some of the equipments in the form of isolation transformer or the harmonic mitigation transformer, some circuits which are dedicated to sensitive equipment, and the conditioning units. So if we do it, what has happened in the result, if you see it, the limit was 5% for the THD. So the THD has been brought down from 8.2% to less than 3%, and no equipment interference is now having, and improved patient safety was accomplished. So yes, case study 3 also shows that if you take proper measures, obviously the harmonics will be brought down with the corresponding standard. There are something which is known as interharmonics and subharmonics. What are these? Interharmonics means the frequencies that are non-integer multiple. So when we talk about 2, 3, 4 and 5, they are basically the integers. If you have non-integers like in the decimal point 2.5, 3.5 and so on, so they will be resulting in the interharmonics. So these are generally caused by the devices such as cycloconverters, arc furnaces and wind turbines. These cause flicker and equipment malfunctioning. So the measurement challenge is due to non-synchronous sampling. So when these non-integer multiples of the fundamental frequencies are present, they are known as interharmonics, and it is a very challenge to measure it because the sampling is not good. It is a non-synchronous sampling is there, because if you have the integer multiple, you can get the synchronous sampling. Subharmonics means the frequency is below the fundamental frequency, because when we know that the fundamental frequency is the one which is dominating, but if the frequency below that, for 50 hertz system, if you have certain things where we are 30 hertz or 20 hertz, then they will be having the subharmonic. So it is below the fundamental, and it is generally the fractional harmonics. Like for example, if you have fraction 1 by 2 multiplied with 50, so it comes to be 25 hertz, which is the harmonics. These are common in static volt ampere reactive compensators and the R furnaces, and these are caused because of subsynchronous resonances which are present in the power system. This is particularly problematic for rotary machinery. So you have the synchronous machines, generators or the motors. So they are basically impacted by the subharmonics, where the fundamental frequency less than that, the harmonics are there. Important note is standard harmonic analyzer may not detect interharmonics and subharmonic accurately. So this is a challenge. Whatever the equipment you are using, the harmonic analyzer, they are capable of detecting only the integer multiple of the fundamental frequency, but not the fraction or the non-integer multiple. So that is basically a challenge. Now, the smart grid nowadays is generally used, and if you want to find the power quality of these smart grid in the distributed generation, whether you have solar inverters, wind turbine, which will be introducing the new harmonic pattern. So the grids are basically modernized. So if you see here the microgrid system, which is the combination of solar, wind, electric vehicle, battery storage system. So microgrid system, which is having so many renewable energy sources as well as the battery sources, they will be introducing the new harmonic pattern. So if you have this new harmonic pattern, then you will also have the high harmonic content, which are basically produced by these vehicle charging, and this will again contribute to the previous harmonics which are already there in the system. And these grid technologies are the one where we can have the real-time monitoring. Real-time monitoring is always required, what harmonics are present, and adaptive filtering techniques has to be used. Coordinated harmonic mitigation need to be done so that we can counter if detect those unnecessary harmonics which are present in the advanced grid systems. So we have to do the resonance analysis in harmonics, whether it is a series resonance or parallel resonance, given by this formula of series and the parallel resonance. So these are basically the most fundamental formula that we use generally for resonance calculation. So resonance is again a concern because the amplification of harmonic voltage and current is basically done. Equipment will be overstressed, system instability will be taking place, and there will be capacitor failure. So the prevention methods that we use is basically the scan the frequency, detune the filter, system impedance analysis you do it, capacitor bank design modification need to be done. So if we do this, some prevention method we can take into account, and the resonance condition can be counteracted. So series and parallel resonance, which are more general in the system because there will be amplification of the current and the voltage. Now, the existing emerging technologies and challenges which are basically using, like the wide bandgap semiconductors comprising the silicon carbide and gallium nitride devices, this will be enable high switching frequencies, and there is a potential for a reduced filter requirement. So new EMI challenges at higher frequencies. We use artificial intelligence nowadays a lot in power quality. So AI-based harmonic prediction can be done, mitigation, machine learning can be incorporated for filter design, predictive maintenance can be done for harmonic analysis. We can also have the grid scale energy storage, large scale battery systems and harmonics, grid forming versus grid following inverters, harmonic coordination in microgrids. So the research that generally take place in the harmonic distortion analysis, its measurement, as well as the new microgrids which are coming, advanced technologies which are coming. So yes, artificial intelligence is playing a very important role, and use of the advanced semiconductor devices also plays a good role. Standards we need to follow, whether we need to update the standard IEEE 519. So new measurement techniques are going to come, revise limits for modern load, and improve guidance will be there for the distributed resources. Other standard IEC 61000 series update is there. Future consideration has to be done for high frequency harmonics, the harmonic limit and probabilistic harmonic assessment. So standards are also evolved for the harmonics. The more and more the modern power system is getting uh, having advanced features, the standards whatever is used, they are also getting updated, and the limits are basically again pre-specified. So what are the key takeaways from this discussion? So we understood the harmonic distortion is inevitable with non-linear nature of the load, but can be managed effectively. Proper assessment has to be done using the measurement like THD, TDD, and individual harmonic analysis, which are crucial. Certain standards are available like IEEE 519, IEC 61000, which provide essential guidelines to have the acceptable limit. You have to choose some appropriate solution based on the cost, effectiveness, and the system requirement to mitigate these harmonics. Consider the harmonic from initial design phase to avoid costly retrofits. So whenever we are designing the system from there itself, we need to consider this impact of the harmonics. Stay updated with emerging technologies and evolving standard. So always the standards are getting evolved and new technologies are going to come day by day. So we need to stay updated. Summary, if we take harmonic distortion is a critical issue in modern power electronic system. It caused primarily by nonlinear load and switching device. So this nonlinear load and switching device are the one which are generally present in the modern power electronic system, which are the main reason for the harmonics. The range of the equipment effect can be there. It is overheating, reduce efficiency, and we have to obey the compliance, otherwise there will be non-compliance of and the system instability issues will be there. Comprehensive measurement has to be done using these standards, having the THD level, the TDD level, and the IHD in accordance with the standard. Multiple mitigation strategies are available in the form of passive filters, active filters, PWM techniques. Understanding and managing harmonics is crucial for reliable, efficient, and compliant power system. And future development will be using wide bandgap semiconductors, the AI techniques. Smart grids will be continue to evolve in the harmonic management strategies. So we have the practical design guidelines. Essential design rule is always perform the harmonic analysis before installing the power factor correction capacitors. Use the K-rated transformer for loads with significant harmonic content. Consider the line reactor as cost-effective first step for VFD installation. Plan neutral conductor sizing carefully in system with triplen harmonics, and implement harmonic monitoring at critical point in the system. So these design rules need to be obeyed. And we need to remember one thing is prevention is always more effective than the remediation. So from the design stage only, we have to take care of these harmonics at different devices, different points, and different equipments. Some of the references you can look about having the IEEE standard, ISS standard, and some of the famous book on electric power quality and harmonics. Some handbooks are there, and standard given by IEEE and SIGRE. Online resources are also available from the Power and Energy Societies and Harmonics and Quality of the Power magazine. So this was the introductory lecture on power electronics. We have introduced the power quality issue in the previous lecture. This lecture we have mainly focused on harmonic content, and next lecture we will see a little bit more on how the power factor control is done and why it is important. Thank you for now. See you in the next lecture.